So students, I request that we begin the lecture now. Today we are going to look at the bonding, chemical bonding, and we are going to confine ourselves to the covalent bonding and the ionic bonding. Now, this lecture is supposed to have started on Monday, but you had a holiday on that particular day. So this is something we are supposed actually to have covered in four lectures, but already the first two lectures are gone. Now we have today, I think normally we only cover this morning lecture. We need to find a way of compensating for the lost time, and that one we can discuss with you and see whether we can create some time and recover the lost time. Now, the first slide here up to the 12th slide, this is actually basic information talking about the topics and the concepts to be covered. And if you allow me, I will skip that because you'll see it in your profiles on the lectures. So I want to go straight to the content, if that is agreeable, students. And the content starts with, I think, slide 13. That is where I want to go to. So this is it agreeable that I go straight to the content and start there?
Yes.
Thank you very much.
Yes.
So we straight away start with the chemical bonding, because when you talk about chemical bonding, this is actually where we are talking about the ionic bonding, the covalent bonding, and we'll also be talking about metallic bonding, just to mention. And by definition, we say that a chemical bond is a strong attractive force that exists between certain atoms in a substance. And basically, we have three types of chemical bonds. These are the ionic bonds. We'll spend some time talking about ionic bonds. We also have covalent bonds, and we have metallic bonds. So those are the three main types of chemical bonds that exist. I know in the past you may have talked about the van der Waals bonding system. The van der Waals is not a chemical type of a bond. It is a physical type of attraction between molecules that possess some particular properties. It is actually not a chemical bond, but a physical bond. And that is why we are saying that there are three main types of chemical bonds, and the types are ionic bonds, the covalent bonds, and the metallic bonds. And here we are saying that metallic bond is simply an arrangement of atoms where the valency electrons are circulating through the crystal, attracted by a sea of the positive charges of the metals. Because you remember that when we have negative charges, which are the electrons, and the positive charges, which are the nucleus, then we would have what we call some electrostatic attraction. And this is actually happening in particular atoms. So these are not atoms of different elements, but atoms of the same element. For example, for metals, we end up getting what we call the metallic bonds. Now, the properties of substances, for example, the sodium chloride. When you talk about sodium chloride, here we are talking about an example of an ionic bond, is determined by the chemical bonds that exist between the particular atoms that form that particular compound. And we start with the ionic bond. And when we talk about the ionic bond, this is a chemical bond formed by the electrostatic attraction between positive and negative ions. The difference between ionic bond and metallic bond is that in ionic bond, we have a negatively formed or a negatively charged ion and a positively charged ion, which actually attract one another. In metallic bond, we have a sea of electrons immersed in some positive charges, which are the nucleus, the positively charged nucleus. So when we talk about an ionic bond, which is one of the issues of focus today, we will look at the complete transfer of an electron from one atom to another. So that's why we are saying that it is formed from the complete transfer of valency electrons from one atom to another. And usually this happens between metals and nonmetals, because if you look at the electronegativities of metals and nonmetals, they are so big. The difference is so much that it is going to ensure complete transfer of electrons from one particular species to the other. So some of the particular examples that we can give for ionic bonding, here we can say that an ionic bonding forms when one or more electrons are transferred, we have already said this, from the valence shell of one atom to the valence shell of another. And a very good example is what we are showing here. Now, if you look at, you will allow me admit some students as we continue. Have I admitted this one? Let me see. I think I have. So a very good example here is where we have sodium. So this is sodium, and you know sodium has atomic number 11. And normally we have 1s2, you pardon my handwriting, 2s2, 2p6, and 3s1. That is what we have. Now, it is reacting with chlorine. You know, for chlorine here, it is 17. So we have 1s2, 2s2. I want to write it like this so that I can show the proper electronic configuration. 2p6. Let me admit somebody here, students. Thank you. Then we have 3s2, and 3p5. Now, if you look at these two configurations, one for sodium and the other one for chlorine. Now, this is the valency electron in sodium, and these are the valency electrons in chlorine. The reason as to why we have transfer of electrons, sorry, the reason as to why we have transfer of electrons from one species to another is to ensure that the remaining species have or acquire a complete noble gas configuration. Now, what you can see here, students, up to that, sorry, that is the electronic configuration of neon, and that is why this electronic configuration of sodium is written as neon, then 3s1. The 3s1 can be seen here. Likewise, if you look at what we have here for chlorine, that again is the electronic configuration of neon, and that is why it is written as neon. So 3s2 and 3p5. So what is happening here is, if you take this electron completely and transfer it, the moment you transfer it, you actually remain with a neon configuration, because the 3s also goes. And that is why you have this electron here being completely transferred all the way to chlorine, so that now chlorine is not 3p5, but it is 3p6. Now, when it is 3p6 now, it gives a different electronic configuration. This is actually going to be argon, all right? So the complete transfer of electrons here is going to ensure that we do have an octet or a noble gas configuration. And in the process, what is happening? Once an electron is completely lost from sodium, now that sodium becomes cationic in the sense that it becomes positively charged. And that is why here you have a positive charge. On the other hand, when chlorine acquires the one electron that is released by sodium, it acquires a negative charge. And that is why we have a negative charge here for chlorine. So what is formed here is a cation and an anion. This is the anion, and this is the cation. So the anion and a cation have different charges, and therefore there's going to be electrostatic attraction between these two, and in the process, an ionic bond is going to be formed, simply because this is a bond formed by ions which are electrostatically attracting one another. And we say that the atom that transfers the electron becomes a cation. For example, here sodium is a cation because it is the positively charged particle. And the atom that gains the electrons becomes an anion. In this particular case, it is the chlorine, which is an anion because it becomes positively charged, negatively charged. So we move on. We go to what we call the Lewis dot structures or the Lewis dot symbols. Now, if you remember your lower levels of learning, that is the high school, the secondary school, depending on where you were, you used to write the electronic configuration, and then for you to show the arrangement of those electrons, you would actually put some circles to mean the energy levels, and on those circles, you'd either put crosses or dots to show the arrangement of electrons in the first energy level, second energy level, third energy level, depending on how many energy levels have electrons and depending on the element that you are talking about. Now, that one was the beginning of what we call the Lewis electron dot symbol. We say that the Lewis dot electron symbol is a notation in which the electrons in the valence shell, in this particular case, we are interested in the outermost electrons. So the electrons in the valence shell of an atom or an ion are represented by dots placed around the chemical symbol of the elements. And how do we do this placement? These dots are placed on one side until all the four sides are occupied. So as you increase the number of electrons, then you arrange them in such a manner that you start with one dot, two dots. That is as you move from the left to the right of the periodic table. And that one is illustrated in the slide that follows. This may be very small for you to see, but I will explain. Now, if you look at what we have here, we have, for example, lithium. Lithium is 1s2, 2s1. And in this particular case, this is where we have the valence orbital. So this one here is the valence electron. And for that case, you can see we have written lithium and there is a dot here. Now, this dot stands for the valence electron. This is the one electron that you can see here. The innermost electrons are actually carried in the symbol of the element. So the moment we write lithium, now this one carries the outermost electrons, and that is 1s2. So that what we show as a dot are the valence electrons alone. Now, when we come to beryllium, you know it is 1s2 and 2s2. So the moment we write beryllium, Be, that one already carries the innermost electrons, and the innermost electrons are these ones here. And therefore, we are left with two valence electrons, which if you look at this diagram here, we have a dot here and another dot there for the two electrons. Again, when you move to boron, this is a 1s2. Let me just do away with the drawing so that I can continue drawing. For boron, you have 1s2, 2s2, and a 2p1. Now, these are the valence orbitals, the outermost electrons. These are the valence orbitals. So when you write B for boron, you have already covered the 1s2. So the valence electrons are shown by 3 dots, which you can see here. And then it continues for carbon, nitrogen, oxygen, fluorine, and neon. Then if you look at the third row of the periodic table, or the third period, So you have sodium, because sodium is an S1. You have magnesium, magnesium is an S2. Then you have aluminum, aluminum is S2P1. Then you have silicon, silicon is S2P2. Then you have phosphorus, which is S2P3. Then you have a sulfur here, which is S2P4. Then you have chlorine here, which is S2P5, and then argon, which is S2P6. So this is the arrangement of the dots depending on the number of electrons that you have in the valency shells. Now we continue, and examples. Now the examples that I'm showing here is to do with the formation of ionic bonding. So here I am illustrating the complete transfer of electrons, for example, from magnesium to two fluoride ions so that we can form magnesium fluoride. So use Lewis dot structure to represent the transfer of electrons from magnesium to fluoride atoms to form ions with noble gas configurations. So you know that this magnesium that you see here, this magnesium that you see here is an S2. That is an S2. And the fluorine that you see here is it is S2, I mean S2. Let me do away with this so that I can write well. This is an S2 configuration. This is a S2 P5. This is also S2 and the P5. So what is going to happen here? Now, this requires one electron to become a P6. This one requires an electron to become a P6. So where are these electrons going to come from? One electron is going to be added to a fluoride ion, and another electron is going to be added to a fluoride ion. So that in the process now, what we are going to get, now is an S2 and a P6. And in the process, if I can put this in the process, that one is going to become negatively charged. Similarly, this other fluoride here will be S2 P6. And again, in the process, it becomes negatively charged. So you can see there are two negative charges. But now what happened to the magnesium? The magnesium here has lost the two electrons in the 2s orbital, and therefore you are going to have magnesium with a charge of +2. So this +2 is going to cancel with the two negative charges in the formation of magnesium chloride. So in the process, we can actually monitor what is happening. If you have the electron dot symbol of fluorine here, you can see there is an illustration of movement of one electron from magnesium all the way to fluorine. And in that case, you end up forming a fluoride ion with a negative charge here. And this one has a noble gas configuration. The other electron from magnesium, again, you can see it is illustrated that it moves all the way to the other fluoride ion, and it ends up forming this kind of a configuration. So that is actually what we have. Now, this magnesium here has lost the 2s energy shell because the two electrons have already been lost. So that is how we can illustrate the movement of electrons from one species to another when we have formation of an ionic bonding. So we continue, students. There is an exercise here, and the exercise here requires you to use Lewis symbols to represent the transfer of electrons between the following atoms to form compounds. Important to note, if you look at calcium, you know calcium is an S2. and bromine is a P5. Bromine is one of the halogens. Therefore, we can say that this calcium here is a divalent atom, while bromine is a monovalent atom. Monovalent here, we are talking about the number of electrons available for exchange. So here, this one can accommodate an extra electron, and this one can give 2 electrons. Therefore, the formation of this will involve 2 bromide atoms and 1 calcium atom. And then they are going to exchange electrons such that we are going to have formation of, let me pick a pen here. We are going to have formation of calcium bromide. So this one is similar to what actually happened in magnesium chloride fluoride above. Now the potassium and iodine, the formation of potassium iodide, both of these are monovalent particles, and therefore is going to be in a ratio of 1 to 1. So the bonding here is going to be similar to that of sodium chloride. Now magnesium fluoride here is similar to what we have shown in the previous. Is it what we have shown in the what do we show in the previous? In the previous, yeah, it is actually shown. So magnesium and fluoride, this one we have already done, you can see. Then we have aluminium and chlorine. Aluminium is trivalent, chlorine is monovalent. Aluminium and oxygen, aluminium is trivalent, oxygen is monovalent. Maybe if I can very quickly give the chemical formula for the species formed. This one I have said, let me just get the pen again, sorry. This one I have said is calcium Br2. This one is potassium iodide. This one is MgF2. This one is going to give us AlCl3. And when you expose it to some high temperatures, you actually get a dimer, which is Al2Cl6. Now, this one is what we call Al2O3. Remember, we have got what we call the exchange of valencies. Alexa, you have raised your hand. Can we talk to you, please?
Yeah, I wanted you to repeat the conditions you said in which aluminium chloride forms a dimer.
It forms a dimer when it sublimes. Okay?
Yeah.
When you expose it to temperatures, it is going to sublime. And when it sublimes, it actually exists in this particular form. Just to mention the chemistry of aluminium chloride. Is it clear? Is it clarified?
Yeah.
Thank you. Yes, Hamed, you have raised your hand. There are 2 students who have raised their hands. Can we hear them?
Yes, I wanted to ask for
raise your voice, please.
Oh, the previous slide.
Yes.
For magnesium.
I go to the previous slide.
Yes.
Yes, we are here.
How come we don't show okay, now that magnesium has become an ion, it's gotten another set of valence electrons.
This
one. Yeah, how come we don't show?
How come we don't show what?
Since now magnesium it's gotten a new form, new valence. Yeah.
Very good. Let me explain that. Now, look, let me write this. Thank you for that very important question. You know, magnesium. Let me write it. Magnesium here as a 1s2 2s2, you pardon my bad handwriting, 2p6, and then 3s2. Are we together there? That is the electronic configuration of magnesium. Now, when we are writing the Lewis dot structure, we write Mg. Now, this Mg already stands for this configuration up to this particular point. And then the two electrons are shown here. There is an electron there and an electron there. I hope we are together up to that point. Now, what happens here is this. These are the electrons that are supposed to be shown in the dot structure. Now, in the transition from magnesium to magnesium 2+, these valence electrons are lost. So what we remain here with is Mg2+. Why are we not showing any electrons? Because the electrons we have shown where they have gone to. They have been transferred completely to the fluoride ions, and that is why we are not showing any electrons here. It has lost the electrons. In fact, what is remaining here is only this type of configuration. I hope that is the clarification you wanted. And
yes, thank you.
Very good, very good. There was another hand. Yeah, there are other hands. Those students who have raised their hands, can you talk?
Okay, for me, on this question that Asna asked.
Yes.
Yeah, if magnesium has lost the 2 electrons.
Yes.
Yeah, like for acquiring the new configuration, why
Yes.
can't you write on the last shell, because it's no longer having these 2 electrons?
Yes.
So its new configuration is these 8 electrons on the outermost shell.
This
Yeah, why can't you write because it has all the 2 electrons, it means its new valence shell electrons are 8.
Yes.
Why can't you write them instead of writing the magnesium?
It doesn't have any valence electrons at this moment. The valence electrons have completely been transferred. That's why we are not writing any electrons here, because the dots here represent the valence electrons. In this configuration, the magnesium does not have any valence electrons. They have already been transferred, and that is why we are only writing this. Is it clarified?
Yeah.
Yes. I have seen other students raise up their hands. Another student, please. I saw 4 hands. Only that I can't know who, because of the way I've displayed my screen. Can we have another question?
Sir, so if the atom is diatomic, you represent it here twice, if like that.
If it is?
Like fluorine is F2. So here that's why we have represented it twice.
Fluorine is?
If it is diatomic.
It is
like
divalent. It is divalent.
Yes.
Actually,
sorry.
What we are saying here is, let me explain that again. We have magnesium, okay? And we have fluorine. This one is monovalent. That one is monovalent. This is divalent. And what do we mean by this? This magnesium here needs to lose 2 electrons. That's why we are saying it is divalent. And this fluorine here needs to acquire only 1 electron. That is why we are saying it is monovalent. And remember, when we have formation of ionic compounds, the formula comes from exchange of valences. So the valence here is 1, the valence here is 2. So these 2 becomes here, and this one comes here, so that we have magnesium fluoride. Now, don't confuse this one to be a diatomic molecule. It is not a molecule in the first place. It is an ionic lattice. So we are not calling it divalent, diatomic. And now that one can be illustrated very well when you actually follow the movement of electrons. And how do we follow the movement of electrons? We have said that this magnesium here is ready to lose 2 electrons. And the 2 electrons to be lost are this electron here and that electron here. Now, a fluorine is ready to accept 1 electron. So if this fluorine here accepts this electron, you'll realize that magnesium will still have 1 more electron to give. And therefore, it requires another fluorine atom to come and take that electron. And that is why we have 1 magnesium here taking 2 fluoride ions to form magnesium fluoride, as I have illustrated. I don't know whether that has been clarified to the student who had asked the question.
Yes.
Any more questions? I saw various hands. If all the issues have been clarified, can we move on?
Yes.
Yes.
Thank you. So we go on, and I have explained how you can look at this from the formula for the chemical compounds. Then you can get to know how you, but simply just write the Lewis dot symbols, and from the Lewis dot symbols we'll see how many electrons do we need to transfer and how many electrons do we need to accept. Yes, Hamed, you have raised your hand again.
Sorry, I just wanted to ask if there are maybe like you have bromine appearing twice, can you just put the 2 or you must show it appearing twice?
Bromine is?
If like in the previous one when bromine was appearing twice, or here chlorine is appearing thrice with aluminium, can you just put a 3 or you have to show all 3 chlorine atoms?
What I am writing here is the formula for the compound. You see, for you to illustrate, you'll actually show how the arrangement is.
Oh, okay.
You will have to show how, just what you are supposed to do is what is shown in this particular slide here, how the arrangement is. All right?
Okay, thank you.
This is what is required of you in this exercise here. So thank you. So let us look at the energies that result from ionic bonding. And we can say that the energy involved in these compounds will help us understand why some bonds are formed while other bonds are not formed. And here we talk a little of the bond energies. And for us to explain this, we need to know what processes are involved in the formation of an ionic compound. So bond energy can explain why some molecules form ionic bonds while others form covalent bonds. And the energy to remove an electron, we have seen that this is the ionization energy, while that which is required to add an electron is what we call electron affinity. Now, both of these actually are processes that require energy, and therefore they are endothermic processes, and that is what we are saying here. The combination of ionization energy and electron affinity is still endothermic in the process that because these two processes require energy. But now when 2 ions come together to form an ionic bond, some energy is released. And the energy released is actually a lot more than that which was involved in the ionization processes. And therefore, the overall process is going to be exothermic. Actually, what happens here is the preparation of the ions, because you have a sodium and you have a chlorine. This sodium has to be transformed from sodium to sodium plus, and this chlorine has to be transformed from sodium to, from chlorine to a chloride ion, that is chlorine minus. So those 2 processes actually require some energy. And then after that, the 2 differently charged particles will come together, and when they come together, some energy is going to be released to the surroundings, and that is what we are calling an exothermic process. So if the extent of bringing the ions together is greater than the extent of forming the ions, then we are going to have an overall exothermic process. And that one is actually explained in the slide that follow. And here we are talking about the lattice energy, which is the change in energy that occurs when an ionic solid is separated into gas phase ions. We are going to see, for example, when we are following the formation of sodium chloride. This is what we call the energy of the formation of crystals from ions. It is used to estimate the strength of bonds. Just one minute, students, I'm coming back. Sorry, I'm back. So it is used to estimate the strength of bonds in ionic bonds. And what we know is that when we talk about the lattice energy, it is not easy to measure it. It is not easy to measure the lattice energy directly. And therefore, we can monitor the energy changes that are as a result of the steps that take place when we have formation of the ionic compounds. And the steps are actually illustrated in this particular slide here. You can see one, an ionic bond between two atoms is actually formed in two main steps. One, an electron or a number of electrons are transferred between two separate atoms to give ions. For example, if I may write this, for example, you have sodium here, and you have a chlorine here. Now, these are in their natural state, but in their natural state, they still require some exchange of electrons. So the first thing that we're going to have is the transfer of electrons. So we are going to have an electron transferred from here to chlorine. And what is this going to form? This is going to form sodium plus and a chloride ion. So once these are formed, this is actually what we are calling ions here. The ions here, we have a cation, and then we have an anion here. So once these ones are formed, these ions attract one another to form the ionic bond because of the electrostatic attraction between the oppositely charged particles here. And these two processes actually occur simultaneously. And we can illustrate that further looking at the specific energy changes when we look at this diagram here. For example, we are saying that to find the lattice energy for sodium chloride, we can use the following steps. And where are we? This is where we are starting. So this is the first step. We have 1 mole of sodium and 1 mole of chlorine. Now, some energy is going to be injected here. Some energy is going to be required so that an electron is transferred from sodium to chlorine. So when energy is required, now that system is going to acquire some higher energy because you are already injecting some energy into the system. And therefore, you can see this step 1, this amount of energy is required. Now, this is positive 147 kilojoules because this is what you need to inject into the system so that you can achieve complete transfer of an electron from sodium to chlorine. And therefore, if you look at what we have here, the energy content of the sodium ions and the chloride ions is going to be higher by 147 kilojoules. Now, then something else is going to happen. Step 2A, we have these ion pairs here. These ion pairs are forming. There is now the electrostatic attraction of the two negatively charged pairs. And that process actually is going to generate some energy to the surroundings. And the energy involved here is 493 kilojoules. It is negative because now this energy is released. So in the process of attraction, they then form a sodium chloride lattice. They form sodium chloride lattice. In fact, what you need to know is that these are in gaseous form. These are in gaseous form. Then once a lattice is formed, further energy is released. And this is actually illustrated in step 2B, which is actually the 293 kilojoules. So what are we looking at? We are moving from here all the way to down here. That is what is illustrated in step 3. That means that when you take 493 and 293, then what you are supposed to get is this 786. Now, but if you look at the beginning point is here. If you look at the beginning point here, and you are just coming down, here, and you compare with this point here, from here, and you are coming down here. These are two processes. Now, this one is what we call a direct process, and this is what we call the step-like process. Meaning that now, if you take negative 786, this 786 here, what is this? 786 plus, these are positive energy here, 147. It is supposed to give you the amount of energy which is absolutely involved in the formation of a sodium chloride lattice from the time you take 1 mole of sodium and 1 mole of chlorine, and you end up forming a solid sodium chloride particle. Now that process, yes, Kadhambi, you have raised your hand. Please ask your question.
Yeah, I was asking, is it that only step 1 is endothermic?
Yes, step 1 is endothermic. All right, energy is required here. This is the energy of preparation. When you are moving from a neutral atom, these two atoms to charged particles, that is the endothermic process. Energy is required. The other process, yes.
Okay, is there even need for, for those two atoms to undergo step 1, or you can just, in short, what determines if it goes through this long step or just directly? What determines that?
Now, when we talk about a chemical reaction, in most cases, we only present this direct process. All right? When you talk about a chemical reaction, this is the process we show. But in reality, that is not what happens. It is these steps. This is the actual process that takes place. This is the only thing that we show. Sodium and chlorine giving us sodium chloride. That is what we write in a typical chemical reaction. But any chemical reaction, we say that is not as easy as it is presented in the chemical equation. There are steps that take place, and the steps that govern are step 1, step 2A, step 2B, or step 1 and step 2. So this is the actual process which takes place. Why am I showing this process? I am showing this process for us to understand that there are energies involved in the formation of compounds. Now, the energies involved may be energy injected into the system and energy released by the system, or energy absorbed by the system, like in this particular case, or energy released by the system. So this is the actual process that takes place, while this one is the symbol equation that we write. Have I clarified your question?
Yes, thank you.
Good. So we continue. Now, the process of finding the lattice energy indirectly from other thermochemical reactions is what we call the Born-Haber cycle. So the whole of the illustration here is about the Born-Haber cycle. You are following the transitions of the species involved so that you can tell how much is the energy that comes as a result of those particular steps. So what we have shown there is an example of Born-Haber cycle. Further about this sodium chloride, we are still explaining what is happening here. So we are saying that one, this sodium,
Okay.
yes.
On that, you say that the whole cycle is the Born-Haber cycle. But
Yes.
is the Born-Haber cycle excluding the direct one getting the exothermic reaction of negative 600 something?
Forget, let me show you. Now, what we are interested in, just a moment. What we are interested in is this route. From here, we move here, we move here, and we move here. That is actually the Born-Haber cycle. Okay? We are following the thermochemical equations and the steps that are followed so that we can determine how much energy we get from the whole process. This is for purpose, yes.
Okay. So if you're told to give the Born-Haber cycle of the bonding between the sodium and chloride, you just give this one, you don't give this one.
You give the complete one, you give the complete one. You
even
also
that one.
Yes, it is important for following. Because you see, there are two things that may happen. One is the direct.
Oh.
One is the direct, which is the symbol equation that we know. And then the other one is the step like the actual process that takes place. And for you to fully illustrate, just so that we are moving from the reaction of sodium, we are moving from the reaction of sodium and chlorine, and what we are forming is what? Is this. Now, what is the path followed? Now, the path followed is from one, you move that way. You understand what we are saying?
Yeah.
Illustrate, we are just moving from here to here. But what is the actual process? The actual process are now these steps here. That may look complicated, but not that complicated. Because they actually justify. These steps here, they are going to justify where this energy is coming from. Okay?
Yeah.
That is what we call the Hess law, if you remember the Hess law. So can I continue?
Yeah.
Thank you. So further, we are explaining what again is happening in this slide. The first one is in the formation of sodium chloride. The first thing is the sublimation of sodium. We are moving from the sodium to the sodium atoms. So metallic sodium is vaporized to a gas of sodium atoms, and the energy involved is that. Then that chlorine, because it's already in gaseous form, we break it down into chlorine molecules. When you break it down into chlorine molecules, we say that chlorine molecules are dissociated, into atoms, and they are going to be in gaseous state. Yes, there are some hands. Can I hear what they are saying?
Please, can you go back to the previous slide?
The Born-Haber cycle, this one?
No, the drawing, sorry.
Yeah, this
the
one.
diagram.
Yes,
Yeah.
yes.
So my question is, if sodium has to sublime and chlorine also, like since chlorine is in its gaseous state, and it has to dissociate before the bonds are formed, and energy are released in both processes. Why won't this diagram include those things?
Yes.
Energy.
Yes. Now, let me explain what you have just asked. Now, this process here, from here, this is sodium. Then sodium, this actually I can say is a combined process. Why is it a combined process? because you have sodium here becoming sodium gas. This is a solid, okay? And then you have chlorine 2 being broken down into 2 chlorine atoms. They are still atomic. Then from some energy is involved in this process. Some energy is involved in this process. Then after that, they are actually meant to be ions. And how are they meant to be ions? Still in gaseous state, they are meant to be ions by an electron moving from the gaseous sodium to the chlorine atom to form this one and that. So this step 1 actually is including these steps that we are showing here, only that they are combined, they are inside there. Have I answered you?
Please, like, is the energy release, is it constant or it varies?
The energy released depends on which particular atom we are talking about. For example, if you look at what we have here, patients, just wait until I answer this one. If we look at here, you realize that this is 108. The energy involved is 108, and the energy involved here is 120. So you can look at that. Then there's going to be some more energy involved in the transfer of electrons from the gaseous atom of sodium to the gaseous atom of chlorine. So that process actually is combined in this particular step here. And the absolute energy is going to be an endothermic process. Patients, ask you a question?
Yeah, I've been answered.
Oh, you have been answered.
Yeah.
Yeah, thank you.
Yes,
Yes.
I'm not done with my question.
Yes, yes.
So like, are all the 3 processes endothermic?
Which ones?
Or the dissociation, the sublimation, and the, like, when they turn into from atom to ions? Are all the 3 processes endothermic? And
Now,
if they are, the energy for the, you said they combine the 3 processes, so is it like I don't know how they got that energy there. Did you like subtract?
Now, for you to sublime, what happens? You supply some energy. Okay? Because for you to sublime a particle, you see, you are changing a particle from its solid form to some gaseous form. So you are actually supplying some energy. That is an endothermic process. Then for you to dissociate a chlorine molecule, then you have to provide some energy. Bond breakage is always endothermic. You have to supply energy so that you can break down the molecule of chlorine. Yes, Anastasia?
I wanted to ask if for the 2 to react,
yes,
like in this first step, there is an endothermic, okay, it's endothermic. So does it mean like they're like being dissolved in water or something so they can form those ions? So okay.
No,
or they just react?
They are not dissolved in water. These are gaseous particles. At this particular point, can you see here? Let me show again. Here, both of them are gaseous particles.
Okay.
So they are not dissolved in water.
I don't understand. Thank you.
Yes. Can I continue?
Please, Prof. Like, I'm actually, like, the reason why I'm asking this question is because if they are endothermic, then why, like, to find we usually add the energies. But if they are endothermic, like in this case, they subtracted or they added, let's say, a negative energy to a positive energy. That's why they got the 147. So like I was thinking maybe the dissociation and the sublimation is exothermic. That's why they are negative, and they added it to the when they change
to give you what we are
from
talking
atom
about
to
here.
atoms. Yeah, yeah.
No. Now, what is happening here? Let me tell you what is happening. You know, this is going to be a combination of endothermic and exothermic processes. And the net value is going to be this. There's sublimation here, there's bond breakage here, and then there is the complete transfer of an electron from sodium to chlorine. So those are the three processes. Whenever you are looking at a reaction, what determines the overall value of the energy is the combination of the exothermic and endothermic processes. Those combine and give you the absolute value. If the extent of the exothermic is higher than the extent of endothermic, then the value that you get is going to be negative. On the other hand, if the extent of endothermic is higher than the extent of exothermic, then the value that you get is positive. And if it is positive, it means that the whole process now absorbs energy. And if it is exothermic, means that some net energy is released to the surroundings. So that is actually what it determines. But I'm saying that the processes that I'm explaining here are actually involved in step one. So we begin with the sublimation, vaporization of the sodium to gas atoms. And then we have the dissociation energy required to break down the chlorine molecules. Again, these are going to be in gaseous. Then after that, these gaseous atoms of sodium are ionized. And what is this ionization? The ionization is where you have a complete transfer. You are removing an electron. So we say that sodium atoms are ionized, and the ionization energy of atomic sodium, it is equal to 496 kilojoules per mole. And then you have the formation of the chloride ion. You know, an electron is released here, and that electron is going to be accepted here. All right, ionization energy and electron affinities are happening here. So you can look at these energies. If you follow these energies, then you realize that they are going to give you this value that we are talking about here. Now, when you are following this, you need to realize that for chlorine, there are two atoms that are involved, but for complete combination with sodium, there's going to be only one atom which is going to be involved. And that is where we are saying that the formation of sodium chloride from ions, we have only one. We actually started with one atom of sodium, and we started with two atoms of chlorine, but what we require from that is one atom, and they are going to be formed, they are going to combine, and what is going to be formed is just sodium, sodium chloride. Now, this is a solid form, and this is formed in this process. Let me highlight again. It is, sorry, let me pick the highlighter. These here, they are still gases. So when the solid is being formed, the energy involved in crystallization is actually this energy that is going to be involved here. Yes, Ahmed, you have asked a question?
I just wanted to ask if you could go back to the sodium chloride. If you follow the values, if you'll actually get the 147.
You can try to calculate.
Okay, I've tried, but I've not really gotten the 147.
What are you getting?
Because all of them are positive
148.
values. I'm getting a very large number, so I don't know why.
What are you getting?
Okay, I've removed my answer, but then it was a large number because all of them were positive, so I was just adding them up.
Okay, let me advise you to do this. Revise ionization energy and electron affinities. Then follow the correct signs, whether endothermic or exothermic, and see whether you can get that. And then number two, look at this statement here. Where is that? Look at this statement here. The dissociation energy is for chlorine, 240 kilojoules per mole of bonds, or 120 per mole of atoms. So check the value that you are using.
Okay.
Can I get that? Hello? Check that, and if possible, we can do the discussion further on the platform. Is there where we can interact?
Excuse me, I don't understand.
I said,
Yes.
check those guidelines, the ionization energies and the electron affinities, and then look at these energies and see whether they agree. If they don't, when you go to the Blackboard, is there a platform where you can raise queries with your lecturers? I think I've seen something like that.
Okay, I'm not sure.
I think I have seen something like that. So that we can spare time for.
Or in the WhatsApp group chat.
Yes, or in the WhatsApp.
Okay.
Okay. So again, you can see what is happening here. This what we are showing here as an illustration in form of a diagram. A diagram. So you are starting with sodium solid. We have sodium gas. The sodium is meant to be an ion. Then you are starting with a chlorine molecule. It is broken down into chlorine atoms. The chlorine atoms are further converted into chloride ions, and then they are combining to give us this. So you can see the first one here. Let me pick the highlighter again. You can see the first one here is the direct route. Then all the other steps here are the indirect routes. And when we say in Hess law that these steps, the energies involved in these steps and the energy involved in the direct route, they are actually supposed to be the same. We can check that one and verify. Okay. Now, the properties of ionic compounds. Properties of ionic compounds. Number one, ionic compounds have high melting points and high boiling points. Although not the highest, think from chemistry, it is the covalent bonds that have the highest melting and boiling points. These ones are just high, but now the value will be determined by the atoms or the elements that are involved in combination. So we say that there are two factors that affect the strength of the ionic bond. And these factors are actually given by the Coulomb's law, which is the energy obtained in bringing two ions with electric charges Q1 and the Q2 to form or from infinite separation to a distance R. And let me explain what is happening here. Let me pick my highlighter again. Now, if you look at this equation, E here is the energy, and it is directly proportional to Q1, Q2, the product of Q1 and the Q2, and inversely proportional to the distance R. Where Q1 and the Q2 here are the electric charges of the two. For example, if you have magnesium and you have chlorine, what are the electric charges of this? This is a +2. This is +2. This is a +1 or -1. But now when it comes to this particular equation here, you are interested in the absolute value. You're interested in the absolute value. So R is the distance actually. And that one brings us to this equation here, this equation that you can see here. That's why you can see a K here. This K is a result of the removal of the proportionality sign. Removal of the proportionality sign. And from this, you can also see that when the charge of the ion is high, then you are going to get a high energy. Or the higher the ionic charge, the stronger the force. The smaller the ion, the stronger the force. Why is the smaller the ion? When the ion is small, then the charge is going to be high. And I'm going to be explaining that. Yes, there are some questions asked.
Yeah, I have a question.
Yes.
Is that energy obtained or is used?
Pardon?
Is the energy obtained or it must be used to bring them together?
No, this is the energy for the absolute process. All right? After looking at all the processes that are involved, you are going to get some energy, the resultant energy. Now, the resultant energy is the one that is given here. All right?
Okay. Yeah.
For example, let me go back to the previous. Let me go back to the previous. For example, when you look at the energy that you calculate, sorry, it is this energy that you're going to get. That is the energy we are talking about. And where is that energy coming from? That energy is going to come from all these processes that we are talking about here. So it is a function of all those processes. So that is the absolute energy of the bond that you get.
Yeah, thank you.
So we are here. And we are saying that from this equation, this K is as a result of the removal of the sign of proportionality, because we are saying that energy is directly proportional to the product of Q1, Q2, and inversely proportional to R. And when we remove that proportionality sign, sorry, is when we are going to get our K. So based on that relationship, somebody can predict the relative melting points of sodium chloride and magnesium oxide. And how does that one come? Now, the charge on the ions of magnesium oxide is double the charge of the ions of sodium chloride. Let me explain that. If I pick my highlighter again, you see magnesium as R2 and oxygen as R2. Forget about the charges now. So in the equation here, you are going to have E is equal to 2 multiplied by 2 all over R, and then you multiply by a constant K. Now, this here is very important in comparing that. When you are looking at sodium chloride, when you are looking at sodium chloride, this is 1 and this is 1. Therefore, E will be equal to 1 times 1 divided by R multiplied by K. So holding all the other factors constant, if you compare this one, you know this one will give you 1. And if you look at this one, it will give you 4. So that is why we are saying that because the charge of magnesium oxide is double, its force will be 4 times stronger, 4 times stronger than that of sodium chloride. And that 4 times is just coming from examination of the charges here. Okay? Now, other factors are going to come into play, like the size of the ions. Now, as you move, I think somebody told me that you have not compared the ionic size as you move. Yes.
When you're completing the formula for the energy for magnesium oxide and the one for sodium chloride,
yes,
you say you're keeping the K and the R as the constants. So you
yes,
mean that like the distance, you said that the R stands for the distance between the two atoms that are going to combine.
yes.
The distance is always like the distance between the magnesium and the oxygen is always the same as the one between the sodium and the chlorine.
No. When I said that holding the other factors constant, I was basically explaining this point only. Can you see?
Yeah.
I was only explaining this. And remember, there are other things that I'm explaining down here. You understand?
Yeah, so you mean that on this special case, the distance is the same?
It is not the same. We are explaining step by step. And this point here is only talking about the size of the charge. And we are comparing sodium and what? Sodium chloride and magnesium oxide. So this is 1, 1, and this is 2, 2. So when you put that in the equation, you realize that it is expected that this one will be a factor of 4, this will be a factor of 1, and based on that alone, then you would expect the bond in magnesium oxide to be 4 times stronger. And I'm saying that there are other factors that are going to come into play, and you can see I've already started talking about the size of that particular atom or ion. All right. So that statement was because this statement confines us to the size of the charge. So when you only examine the size of the charge, you would expect 4 times stronger if you compare these two. But remember, there is a factor of R and there's a factor of K, again, which are going to be determined by the size of the ions that come together. There was another hand raised.
Yes, Prof, it's me.
Yes.
I've not actually understood how the charge is 4 times stronger in magnesium oxide than in sodium chloride. So could you please repeat once more?
Let me repeat. We are using energy. Energy is equal to K Q1 Q2 all over R. Are we together there? You have seen this equation?
Yes.
Now, in this point here, it is about predicting the relative melting points. So in this particular point here, we are looking at magnesium oxide and sodium chloride. So we confine ourselves to the electric charges here. So for magnesium, the electric charge is 2. So if I change the color, for example, let me just change the color. For magnesium, we are going to have a 2. And for oxygen, we are going to have a 2. And these are these ones here. Okay? It is going to be 2 times 2. So that gives us a factor of 4. While for sodium chloride has a charge of 1, 1. No? Sodium is 1, chlorine is 1. So you have a 1 and a 1. And when you multiply that, it is going to give you 1. So we are saying that if we confine ourselves to the electric charges only, then you would expect the bond between magnesium oxide in magnesium oxide to be 4 times stronger than that between what? Sodium chloride. But then we have said that when you look at this R here is the distance, and this distance is going to be influenced by other factors. And the factors are going to be, for example, the size of that particular ion. And this is what is explained here. But before we go to this one here, I want to ensure that you have understood this first. The question that was asked, how this one is 4 times, is it clear?
Yes, it is clear.
Okay, then we go to the other factors that affect, and the other factors that affect are the size of the ions, and the size of the ions here are actually going to affect the R. Are going to affect the R. Remember here, we are only talking about Qs, Q1 and the Q2. Here we are now talking about R, and the R is going to be affected by the size of the ion and the size, the size of the ion. Now look, last time you told me that the periodicity of the ions was not discussed, but I'm going to mention it. I'm going to mention it here very slowly. Now, when we talk about the atoms, as you move from left to the right, you would expect one, the atomic size is increasing. Is decreasing. Is that what you said? There is decrease in atomic size as you move from left to the right of the periodic table, and this was attributed to the increase in the effective nuclear charge. Is that clear?
Yes.
Now, similarly, the ionic size is going to behave the same way. The ionic size is going to behave the same way. As you move from left to the right of the periodic table, the ionic size is going to reduce. The ionic size is going to reduce. So, if I say a little bit about that, so the behavior of the atomic radius and the ionic radius is the same across the period and down the group. The only difference that is worth mentioning at this particular point is this. If you compare sodium, and the sodium plus, just for clarification, which of these two is going to be smaller than the other? Now,
Sodium plus.
the sodium plus is going to be smaller than the other, isn't it?
Yes.
Yes.
Yeah.
Yes.
Why?
It has lost one shell.
An electron is lost, isn't it?
Yes.
But the number of protons remain
The same.
the same. So there is what we call increase in the effective nuclear charge. Do you understand that?
Yes.
And because of the increase in the effective nuclear charge, that particular species is pulled closer to the nucleus. And that is why when you compare the two, the size of this one is smaller than the size of this one. However, when you look at fluorine, and the fluorine minus, what can you say about the sizes of these two?
Fluorine negative is bigger than the fluorine now.
Very good. Why?
Because it has gained 1 electron.
And what does this 1 electron mean?
Yeah, it's increasing we are having more electrons compared to the protons, which means that the effective nuclear charge will be less compared to this one.
Very good. The other point?
There's also an electron repulsion.
There is also electron
repulsion.
Very good. Very good. So those are the two issues, the electron repulsion and the decrease in the effective nuclear charge. So basically, you people know the trends in the ions. Yes, there's another question raised here. Ahmed?
Sorry, sir, I forgot to lower my hand, sorry.
Oh, that's fine. So then can we discuss this point here, where now we are talking about R? So based on what I have said, we have sodium and we have magnesium. Then we have sodium sodium plus and magnesium plus, you can see that there is decrease in the size of the particle in that direction. There is also decrease in the size of particle in that direction. I have explained that. And that is why we are saying that the size of sodium here is larger than that of magnesium. The size of the sodium ion is larger than that of magnesium ion. And then the size of chlorine is larger than that of the oxygen. You understand why?
No.
Compare this and that in the periodic table. Yes?
Excuse me.
Yes, ask your question.
Are you going to compare the chloride ion and the oxygen ion? Compare using the periodic table, or you're going to use the fact that because they are not in the same group, they are not even in the same period.
Yes.
So what are you going to base on?
When you go down the periodic table, what happens?
Atomic radius.
Atomic radius increases.
Yes. So then what can you say about, let me see whether I can, do you have, let me see whether I can upload a copy of the periodic table just briefly. Just a moment so that I can explain something here. See whether I can get a periodic table from one of my that document I was sharing last time. I'm trying to look for it and see whether I can get a periodic table from there. But maybe I can mention here. Now, when you look at oxygen and you look at chlorine, you know, they are not in the same period, all right? Do you agree with me?
Yeah.
And what happens as you go down a group?
The atomic radius increase.
The atomic radius is going to increase, and the behavior of the radius, I said, is the same behavior of the ion, isn't it?
Yeah.
Yes.
And it is for the same reason that this chloride atom here, which is lower than that of ion, remember here we are talking about extra shells being added, isn't it?
Mm-hmm.
So you would also expect the size of a chloride ion to be bigger than the size of what? Of an oxide ion. Is it clarified?
Yeah.
Very
Yes.
good. Yes. So because the distance between magnesium ions and oxide ions is smaller. Why is it smaller? You see here, you know, magnesium. Let me write again. Let me write this one again. Sorry. So we talk about magnesium oxide, and we have seen that the ion here is small, isn't it? This one is also small. We have explained that, isn't it?
Yes.
It means that now this is two small particles. And if there are two small particles, you'd expect the radius also to be what? To be smaller.
Sure.
All right?
Yes.
Yeah.
Therefore, the R here is smaller for MgO, and the R is going to be bigger for what? Sodium
Chloride.
Sodium chloride. Is that understood?
Yes.
Therefore, can I go back to that equation and explain what is expected? The equation was E is equal to K Q1 Q2 all over R. Now, if I put this for magnesium oxide, we have a K multiplied by 2. You know where these two came from?
Yes.
Multiplied by 2 divided by R. Then for sodium chloride, we have K into 1 into 1. You know where they are coming from? Divided by R. Now, remember R here is a denominator. The denominator here is small. We have explained why. The denominator, the R for magnesium oxide is small. Did we say that?
Yes.
While that one for sodium chloride is big.
Yes.
Now, the question therefore is, when you have a small denominator, then the value that you get is big, isn't it?
Yes.
And when we have a large denominator, then the value that you get is small. What does it therefore mean? It means that while the energy that we are getting here is high, the energy that we are getting here becomes small. And again, that justifies why the force between magnesium ions and the oxygen ions will be far much greater than that between what? Sodium ions and the chloride ions. Are you able to follow that?
Yes.
Very good. Now we have about 7 minutes remaining. We have only done, I think, about 16 slides out of 109. We have to work a way of compensating for these students. But let me see how far I'm going to go. So based on higher charge and the smaller distance for magnesium oxide, its melting point should be significantly higher than the melting point of sodium chloride. This is actually what we have been explaining in the previous slides. So the actual melting point of sodium chloride is 801 degrees Celsius, while that of magnesium oxide is 2,800 degrees Celsius. And you have seen the distance is coming into play, and the charge is also coming into play. Now, the other thing, and let me just explain this and we end at that because of the time. Now, the other thing is solubility in water. The other property is solubility in water. Now, water is a polar solvent. And why is it a polar solvent? Maybe I should also explain this. Let me see whether I'm going to pick, what is the color of water? Let me just use that. You know, water is H2O. And in terms of its geometry, which maybe is something we'll be looking at later in this unit, we write oxygen, then we have hydrogen, and we have hydrogen there. Now, we come to what we call highly electronegative particle, low electronegative particle, and then their electron affinities. So look, this one is, its electronegativity is low. it is low electronegativity, low electronegativity. If it is low electronegativity, it is not able to sufficiently pull the electrons from oxygen. And therefore, if we were to illustrate the sharing of electrons, this is an electron from oxygen, another electron from oxygen, and then we show the electron from hydrogen like that. So the sharing of the electrons here is such that it is going to be closer. It is going to be closer to oxygen than they are to hydrogen, and therefore this one acquires a positively partial charge. This is also positively partial charge, while this is positively negative charge. And that is why we say that water is a polar solvent. It has a dipole moment. It has some charge separation. The charge separation, one part is negatively charged, the other part is positively charged. So when ionic compounds are put in water, the water molecule will break down the crystal like this by attracting the ions in the lattice and pulling them away. So when you bring sodium chloride, remember this carries a negative charge, this carries a positive charge. So there is going to be interference so that this negative gets attracted there and these positives get attracted there. And in the process, that lattice is going to be broken up. And when it is broken up, we are going to have sodium ions and the chloride ions existing separately as mobile ions in solution. So this is when we say that it is an aqueous solution of sodium chloride. Ladies and gentlemen, I may actually not go further than that because the moment I start another slide, it will take me past the time. So can we agree this, that we end at the solubility today? But this lecture, which was supposed to be ending today, is going up to slide 109. We need to find time and see when we can finish this. We are just basically looking at a way of compensating for the lost hours for Monday. Is that something that students can do?
Next week.
Next week. Yes, you know, next week we still have lectures for the 10th week. What I'm requesting for is some extra time, students. Maybe I will consult my colleague and see how best we can handle this. But it is very important that one, we just move slowly and we try to clarify many queries from the students as much as possible. We ensure that we bring all the students on board with regards to understanding the concepts that are being taught. We don't need to brush through the content and leave students not having understood. So we need to also have a compromise on your side so that we can see whether we can create some extra time for me to cover the work that I would have covered on Monday.
Sir?
Yes.
Is next Monday okay?
I'm saying next Monday may not, okay, in terms of what?
The afternoon next Monday.
Yeah, that's one of the things we can look at.
Yeah, we can do that, yeah.
Okay. The afternoon starts from what time?
I don't know, maybe the class can suggest the starting time, but next afternoon,
okay.
Monday.
Okay, yeah. I think we can work with that. And Wednesday, you usually have another two, isn't it? The students? On Wednesdays, do you usually have two sessions or one session?
We don't have, we have one.
You have only one session, eh?
Yes.
Okay, then we will see what we can do, but it is tricky. But
sir, at 3:30, if it's okay, Monday afternoon by 3:30, because I think some people have class the whole afternoon, like from 1 till 3. So 3:30 is an okay starting time on Monday.
Okay.
Yeah.
Then just allow me now, please spare some 10 minutes for me to take the attendance for today.
No problem.
So let me go to the attendance, and in one moment I should be there. Let me look for the attendance. Let me just go there very fast now. Okay, almost there. So which one is this? Just a moment. I need to load. Okay, we start with Y. So I'm going to load the Y. Okay. I'm going to load the Y. So for Y, let me take your attendance. It's loading, just a minute. Just a minute, it is loading. So I think I have to give it time to load fully. Seems to be taking time, but it's almost there.
Please, Prof, I want to clarify something.
Yes.
It's about the enthalpy, like the lattice energy.
Yes.
So I think the reason why they got the 147 was because they actually said, like I was reading a book and the book suggested that ionization energy is usually endothermic and electron affinity is exothermic.
That's why I said the combination of exothermic and endothermic reactions. The extent of each of these will depend on whether the end result is either endothermic or exothermic. Remember, I said that if the extent of the energy consumption is higher than the extent of energy release, then you are going to get an endothermic. But if the extent of energy release is higher than the extent of energy consumption, then we are going to get an exothermic. So what we are saying is actually right. We only need to actually look at each of the steps carefully and look at how much energy is involved in all the processes.
Yeah, but my problem is because they didn't add the sublimation, the energy for sublimation and dissociation. They just added, yeah.
That one, I said that what the step one actually was add other sub steps hidden in them.
Okay.
Yes. So can I take for why Mustafa Abdino?
I'm here, present.
Alice Alango.
Present.
Ane.
Present.
Daniel Bilen.
Present.
Samuel.
Present.
Yeah. How do you pronounce this name, Samuel?
Ishutiman.
Okay, thank you. Leju.
Present.
Then we go to Kembabazi. Lillian. Kembabazi.
Present.
Okay. Lucy Lojore.
Present.
Then we go to Isaac Makuku.
Present.
Then we go to Ivy Moshere.
Present.
We go to Grace Mugambi.
Present.
Angela Murithi.
Present.
Mary Murunga.
Present.
Michelle Murunga.
Present.
Prudence Ndiritu.
Present.
Charity Njuguna. Charity.
Present.
Barbara Omenya.
Present.
Yesh Patel.
Present.
Moses Prince.
Present.
Then we have Cecilia Selempo.
Present.
Then Alexa Umhonza.
Present.
Umhonza, are you from South Africa?
No,
You are from
Rwanda.
Rwanda.
Yeah.
Okay. Then Lucy Wainaina. Lucy Wainaina.
I think she has a connection problem. She's in class.
She's in class, eh? That's good.
Yeah.
Then we have Naiguran Winnie.
Present.
For that class, any student that I have not called? So let me go to Z, the other class. Hope to get there very fast. Anita Ainomugisha.
Present.
Then from there we go to Nicholas Amesowe.
Present.
Obuoge Denver.
Excuse me, sir. Denver was in class. The Wi-Fi went off, so he got disconnected just right now.
Okay.
Yeah.
Then Lydia Edosa.
Present.
Isabella Gardner.
Present.
Lillian Gishengo.
Present.
Hamin Hassan. Al-Hamin Hassan.
Present.
Asna Hassan.
Present.
Maria Janowala.
Present.
Eldin Kisoka.
Present.
Michelle Mogusu.
Present, sir.
Joy Mushemi.
Present.
Anastasia Munjuri.
Present.
Philip Mutinda.
Present.
Alice Odiwar.
Present.
Maria Console Patience.
Present.
Kush Rana.
Present.
Aibekanya Sebata.
Present.
Grace Tuku.
Present.
Lorraine Wainaina.
Present.
Joki Waweru.
Present.
I think that's all. Any student who has not heard their name? So thank you very much, students. Have a very good day. We meet next week on Monday. Bye. Bye.
Thank you, sir.
Bye.
Thank you.
Bye.
Bye.
See you.
Thank you, sir. Have a good day.
Thank you.
Good day.